Our next speaker, we have a series of 3 speakers, and then we have a panel discussion afterwards. Next speaker is Sarah Verhulst. She's at Ghent University, and she's in the Department of Information Technology. And we've already had a little bit of introduction to her work on modeling and the, using cochlear models and deep neural networks. And so I'll let Sarah explain her presentation. So thank you very much. Thanks, Sarah.
Right. Thanks, Sunil, for having me in this session. It's a real honor to be here and to be able to present the work of my lab on personalized hearing loss compensation for next-generation hearables and hearing aids. Before we start, I want to just say that Ghent University has IP patents on the coxine test and some of the technologies I'll be talking about. The EarDetect, which basically covers diagnostics and the hearing aid processing, is currently an innovation project funded by the European Innovation Council, and we will show some intermediate results from an ongoing clinical trial. The work that I'll be presenting today is mostly from the people in my lab. Some of them are here. Fotios and Attila are here, so you can speak to them afterwards too. So what are the challenges for hearing technologies for the moment? Well, we know that sensory neural hearing loss has several aspects. There is the well-known outer hair cell damage, which leads us to wider auditory filters and gain loss. But since recent years, we also know that the inner hair cells and the auditory nerve synapses are an important aspect of sensory neural hearing loss that actually has an earlier onset in the progression of hearing loss. And this has different functional consequences. It leads to fewer independent coding channels because you just lose fibers. And it gives us supra-threshold coding deficits, especially in noisy backgrounds. So if you want to build hearing technologies that compensate for these aspects of sensory neural hearing loss, we need to see how we should do it. So I am showing you an example here of a model simulation of a normal hearing listener at the level of the auditory nerve or input to the brain stem to an expert of a piece of speech filtered in different or like written out at different CFs of that listener. And you can see that the speech looks different, the waveforms at that level of processing. And I'm showing some arrows of features inside these things that we can use to actually inform our perception of this sound. And so when we do this simulation again, but this time for a model of hearing impairment, where we both have outer hair cell loss and 50% of synapse loss, then we can see that these waveforms look different than before. And I think you can also appreciate that it's not just amplification that we are going to need to the acoustic stimulus to be able to bring the hearing impaired responses back to the normal hearing responses. So this is because the features of this sensory neural hearing loss are highly nonlinear, the signal processing that we need to provide to compensate and bring back these two neural patterns to each other is actually going to be very non-trivial. Now, if we look at a classical speech processor, single channel in a hearing aid, then we will see what they typically do is take the audio, filter it in different frequency bands, and then do mostly amplification based on an audiogram and then a high-level compression. And then they recombine this sound back together. Now, this is a very linear way of doing things, and it's traditionally gone through lots of generations of devices. But there are a number of opportunities now that come with the rise in computational power that we have seen in our field. So one of the opportunities is that we as a field at ARO have a lot of experience in modeling the auditory system. For example, colleagues, their names at the bottom of the slide, have over the years developed precise biophysical models of auditory processing that can account for different processing stages, that can account for outer hair cell loss, that can account for auditory nerve fiber deficits. And using these models, we can input speech and simulate how the neural representation of speech is impaired after a certain hearing impairment. Now, these are big computational models and methods, but as you can see, we can then use basically image-based approaches to be able to build a closed-loop system whereby the difference function between the two images or time domain waveforms for different frequencies can be used to train a deep neural network algorithm that can be inserted in a hearing aid. Now, the idea of a closed-loop system in engineering has existed for a long time and has been used by different manufacturers. The only problem is that a good biophysical model has all the nonlinearities of the auditory system included, and that you can essentially not backpropagate through the whole network because the models themselves, you can't reverse engineer them because they have a lot of nonlinearly coupled ordinary differential equations. We have Hodgkin-Huxley models in there, diffusion models for the auditory nerve fibers. So we cannot backpropagate through them. Also, they are very slow to compute. Computational power is in our benefit here. We started modeling these models in Fortran. Then with Python, we can run them on a PC. And nowadays, we just get faster and faster, but it's still not real time. And because they're not real time, you cannot introduce them in a closed loop system or use them as part of a hearing device. So the industry, they still use rather basic auditory models as part of their development cycle for hearing aid algorithms and haven't jumped onto the wagon of incorporating biophysical realistic models, and thereby they cannot really compensate for the combination of outer hair cell loss and auditory nerve fiber loss. Now, but how do we jump this gap? We need to make these models, first of all, differentiable in their equations, which means that we need to reformulate them to be DNN-based. So we basically replace all the equations of the biophysical models by a DNN version thereof, with the idea that that DNN model will perform exactly the same computations as before. The only difference is that it will use elements of DNNs, which in nature are just combinations of equations that can be differentiable. So if we have a DNN version of our model, we can backpropagate through it, so we can find an exact reverse engineered solution. When we insert such models, we can actually close the loop and change the audio of the hearing aid in such a way that you get a perfect numerical solution to this closed loop problem. When we do this, we actually get a speed up factor of over 2,000. So we can now run on a GPU computer these models in real time, and we do this with parallel equations. So we can actually start thinking about signal processing that can go on the next generation of devices. DNNs are also, in terms of chip design and hardware, they are going to be on board of the next generation's hearables and hearing aids. So we can make speech processing that is ready to be cast onto those architectures. So in the end, when we close the loop, we get end-to-end audio processing, and we actually reach target latencies less than 10 milliseconds with the trained hearing aid, so we can actually start integrating it into a device. So I'm first going to talk about these DNN-based auditory models, how we got there. Then I'm going to talk about how we personalize them, and then about patient benefit, first results. So let's unpack this model. As you can see, it's a modular design whereby we have for each part of processing in the auditory system a specific model with different layers and different flavors. I'm going to not talk too much in detail of how we got there. The only thing that is important here is that the processing of the models is still modular. So if you want to incorporate outer hair cell damage, we do this in the first element. If you want to model synaptopathy, we do this in the last element, so they can be fully personalizable because they remain modular. How did we train them? Well, we used our biophysical models and a large speech corpus that built the training data for the neural network counterparts. So we basically take this biophysical model and for the basilar membrane processing, just create training data for a whole speech set and then minimize the L1 error between the neural network model and the biophysical model, and that determines the parameters of this CNN. We do this for the next stage and the next stage, and when we do that, we have to, of course, see that it works. And so we trained it using speech data, but we evaluated the performance of the models using auditory neuroscience and cochlear mechanics data. So to show you on the figures, we have simulated tuning as a function of CF for the basilar membrane vibration. We have the inner hair cell growth curve, and we have auditory nerve growth curves for different nerve fibers. What is important to see is that the biophysical model results are in black, and that in color on top you have the responses of our DNN-based counterparts. So as a proof of concept, we can say that the elements of our neural network model can perform cochlear mechanics equally well than the biophysical models that underlie them, even though their architecture is now completely based on different equation elements, on convolutional neural network approaches, and not on the standard biophysical equations. So it works, and we can take our big model and then compress it again into our normal hearing model and put it back in the loop. And when we do that, we can now create these audio processing methods that are basically there to minimize the difference between the two images, normal and hearing impaired. And so doing that for an example, I'm going to just show you. You can listen to it.
Twitched his shirt sleeve, and he felt a brief burn on his upper arm.
So that's the original.
A second twitched his shirt sleeve, and he felt a brief burn on his upper arm.
I think you can hear that this computational method, DNN-based, just works. And that in itself is, I think, a big milestone, just because it's based on a completely different numerical way of getting there. It's not filtering, it's just doing this end-to-end, audio in, audio out, normal and hearing impaired model, and that's what you get. So it sounds pleasant, it's possible, we can do something with it. Now, the biggest challenge here is not just making this hearing aid algorithm, it is personalizing it to the user. So we need frequency-specific outer hair cell damage and frequency-specific synaptopathy inside this, and the users or the people that we have, we need to use their measures to be able to set these parameters. So how do we do that? We take a step back to the biophysical models, because the biophysical models connect the physiology of hearing, the generators of the EEG and the otoacoustic emissions, to parameters inside that model. And when we personalize this biophysical model based on your physiology recordings, we can then retrain this Connier-based neural network model to have your sensory neural hearing loss profile. So for the audiogram, we can just take classical classifier methods to come up with the basilar membrane parameters that we need. I'm not going to explore this further. So we could just do that based on the audiogram, but I want to show you a little bit more about how we do it with the auditory nerve loss pattern. So we can basically take a synapse loss pattern, frequency specific, and we can make 7 of them as a starting point. but more or less synaptopathy. And then introduce each one of these patterns inside the model, and then use an auditory stimulus to see with each one of these patterns how the EEG response changes. So you can see that with this stimulus, you have a simulated EEG response that varies in size, and the size that it varies with is related to the synaptopathy pattern. This is just simulating. Now we take our user in the loop, we give them the same auditory stimulus, we measure their EEG, we look at the measured EEG response size, and we see with a classifier which one of the simulated responses best matches that one of the listener we just tested. By doing that, we classify them into one out of these 6 synaptopathy patterns. So we use auditory EEG to individualize the biophysical model parameters first, classify somebody to have 1 out of 6 synaptopathy patterns, and then we retrain the model and have a personalized model that both has synaptopathy pattern and an audiogram. So that's how we personalize these models. We place them back in the loop, and now we are going to test how well they perform. So we're going to start with a basic first example of outer hair cell compensation and outer hair cell processing. So we're evaluating the model objectively here, or the algorithms objectively. We're looking at basilar membrane responses to speech for a normal hearing model in black, in dashed for a hearing impaired model. Now we're applying the NAL2 standard processing. You can hear it.
A second twitched his shirt sleeve, and he felt a brief burn on his upper arm.
You can see that the hearing impaired response moves closer to the normal hearing response.
A second twitched his shirt sleeve, and he felt a brief burn on his upper arm.
So from a theoretical perspective here, our Connier-based hearing aid algorithm focused on the same outer hair cell loss pattern was able to restore basilar membrane processing well. So that was an objective evaluation. Let's now see how this works with real listeners. So these are very early results of our experiment. So the listeners we tested had high frequency sloping hearing loss, and they had synaptopathy in the lower bar of the norm population. So in the box plot, you have basically 100 people's EFRs, and then in the red crosses, you have those of the hearing impaired listeners that we tested. So they both have a degree of outer hair cell loss and synaptopathy when we test them. And then we do a classical SRT experiment, speech and noise reception threshold, for a 70 dB speech level for different noises. And then we see the individual data points. So first thing to notice, this is the unprocessed SRT, and from that you see arrows in both directions. In light gray, you see the lines of where the processing did not improve the performance. They exist. And in both cases, you can see in the blue lines the cases where there was a benefit of applying the hearing aid algorithm. So both for NAL and for our Connier-based algorithms, for some people it worked and for others it didn't. But we are pretty similar to null in terms of the success on this objective speech and noise task. So again, this is a very positive first outcome of the results. If you now look at synaptopathy-based algorithms, it's not so easy to evaluate them. You need to look at the auditory nerve. So I just showed the waveform from them, and I'm going to let you listen.
A second twitched his shirt sleeve, and he felt a brief burn on his upper arm.
That was the original.
A second twitched his shirt sleeve, and he felt a brief burn on his upper arm.
So you can notice quality differences there. It's again the model that decided that that's what it was going to do to compensate best for synaptopathy. And then we tested this time first also with the normal hearing listeners, the performance. So here the audiograms are only at the high frequencies, very sloping. I'm just going to put them both so you have the frequency range. So what you can see in 8 listeners, not everybody had an improvement of applying a synaptopathy-based algorithm, but for 3 listeners, there was in fact a benefit. So it is not a one-size-fits-all yet, but we can show that for some people, CS-based processing did give them better performance. For the hearing-impaired listeners, here we didn't amplify, we just used the CS-based algorithm, and here you can also see that there are 3 listeners that benefit from the CS-based processing aside from trying to compensate for their outer hair cell loss damage. So even though we focus on the CS processing, there can be benefit. Now, I'm talking a lot about benefit, but anyone of you who has developed hearing aids knows that there's a lot of individuality, and we definitely need to better understand this data to understand when is the benefit the best, for whom, in which combinations, do we need to add CS processing to OHC or just do CS processing? Well, these are all open questions. It's too early, but I wanted to show you the first results because, you know, it's innovation. So I'm going to summarize here. So what we know from this field is that the biophysical auditory models have now advanced to simulate effects of different sensorineural hearing loss types on speech processing. And so we can simulate computationally the effects of outer hair cell loss and synaptopathy on the speech processing. We can personalize these models using precision diagnostic methods such as EFR, ABR, and DPOEs. And this makes that these personalized biophysical models can be cast into Connier-based neural network versions thereof that can be used in closed-loop systems that are differentiable, personalizable, and that can work for real-time audio applications. I think that part is a very big leap from basic auditory modeling to application, and we are seriously only starting to see the first outcomes of this. This goes way beyond just hearing aid compensation. It is a very good example of a use case, but also noise reduction methods, robotics hearing, machine hearing. All these systems can use biophysical front ends in their features now that we made this computational jump. So our hearing aid algorithms are DNN-based, so they can fit for the next generation of hearing aid processors. They can account for synaptopathy as well as for outer hair cell damage. It gives us end-to-end processing that bypasses sound quality issues in traditional approaches. As I said, the neural network takes audio in, audio out. It doesn't need to filter first. It doesn't need to recombine amplified and compressed signals. So you miss a step in the creation of distortion. You just go from end to end, and you can do it in real time. Now we have the first results that I showed you with patient benefit. It's a first step. The algorithms will be improved. We will learn from how they now actually work. We have a poster on their transfer functions later this week if you want to learn more. But the first experiment we did was just like, okay, it works. We can create samples. We can do testing with it. Let's do it. We picked at the time the methods that we thought at that point were what we could do. And from the results of this experiment, we will now move to the next step and improve and build upon this together with the other actors in the field. So with that, I hope to have given you a nice example of how you can use DNN-based auditory models for closed-loop applications and the next generation of hearing aid design. So thank you very much.
Thank you, Sarah. There's some pioneering work in this area. She's one of the first people to actually do this. So congratulations on
Thanks.
making progress. Brian?
When you presented the results of the evaluation in terms of SRTs, 3 subjects got better with the CS processing, but it looked like a pretty small effect. Was that significant? I mean, it looks like my view of it, looking at those, would be to say most subjects got a bit worse. 3 went slightly the other way, and overall, there's not any clear evidence.
When they got better, they got actually better. So that's a stable result there. But indeed, we have to look into it. In our first insights, I mean, it matters in which classification they were. So as I said, we had like 6 classification degrees. The CS processing worked best for people with sort of moderate synaptopathy, like 60 to 70%. If they had more than that, then an outer hair cell loss-based method worked better. So these are our first insights. We just need to further explore. Yeah, thanks.
Okay.
Go ahead.
Hi, Sarah. Great talk.
Thanks.
I'm wondering how much additional time this would take to implement in a clinical setting, whether that's the additional testing with EFR, ABR, all of that, as well as the fitting process.
Yeah, so for the moment, the CS-based method takes 6 minutes. Of course, you'd have to apply the EEG electrode. And at the moment, we're doing a fit based on only the 4 kilohertz marker. I think in reality, you would want to at least have 2 frequencies in there, one below and one above the phase locking limit. But we're working to be able to use as little as possible diagnostic time to do this fitting. Yeah.
Thanks.
Thank you. Okay, one more.
Thank you for amazing talk. I'm Kazuhiro from Japan, and I feel not only hearing loss, but also hypersensitivity of hearing and hyperacusis is important and need more appropriate aids. And your technique and method can be applied to those aids. I think. How do you think about that?
Yeah, well, if we have a good neural marker of hyperacusis or tinnitus EEG based, and we can simulate that neural response, then you can put it in the closed loop and also design methods for that. But yeah, time will tell if that can work.
Thank you so much.
All right, thank you. Alex, thank you, Sarah. Before we bring up our next speaker, I apologize about the captions at the bottom. They've been trying to fix those. It's a signal-to-noise type problem in the visual world, but we have to keep those on because there are a few folks that need the captions up front with the aids. So instead of turning them off, I think we kept them on. So just bear with me. They are trying to fix it. I'm not sure we'll get them fixed in the next 2 talks. Okay, it's my pleasure to introduce Stefan Launer. I've known Stefan for a long, long time, actually, from IHCon. He's the VP of Audiology and Health at Sonova, Phonak, and I think he's going to talk about this amazing hearing device. I've been working on a deep neural network chip that's in the device itself. So I'll let you take over from here. Thank you.
Thank you, first of all, Sunil, for the invitation to be part of this really great and very inspiring seminar this morning. And I'm going to take us to a more practical application of DNNs and how they work in today's hearing instruments. So I'm going to talk a little bit about the potential and limitations of applying DNN-based algorithms specifically for the purpose of speech enhancement or noise reduction in hearing systems today. And basically, AI is going through a huge hype at the moment, and we see it all over the place, constantly in the media. If I think about our field, the application of AI-based technologies is not that new. We actually started almost 30 years ago in the early mid-90s. People started working on it. And when I look back, there have been two main applications to begin with. One was really speech processing and speech enhancement in the audio field, and the other one was content analysis and scene analysis. So the idea of having a hearing instrument that is kind of scene aware, that Thorsten so nicely talked about, has been around for a while, and we always had different listening programs in hearing instruments that were kind of used for optimizing the processing in different situations. And we started in the 2000s to make the hearing instruments automatic so that they would automatically switch between different settings. And that was one of the first applications of using machine learning type algorithms, classical classifiers in hearing instruments. And I think there is no hearing instrument today that hasn't had these functions for many years, where classic classification systems are applied to identify different scenes and switch the hearing instruments accordingly to apply different settings in different environments. That was one application that has been around for a while. And also the other application of using DNN or neural network machine learning type algorithms to enhance speech signals isn't quite new. When I recently did a search on applying multi-layer perceptrons and neural networks and DNNs in hearing instruments, I realized already around 1990 people started using multi-layer perceptrons and also classic neural network systems in hearing instruments. The problem they ran into was that they never performed any better than the classical noise reduction schemes, single microphone or multi-microphone noise reduction schemes that we had in the hearing instruments. And the reason simply was that these systems that could be trained or could be used and could be computed at the time were simply not powerful enough to really provide any benefit over the classic approaches. This started to change maybe around 2010, when a lot of computational power, a lot of data, a lot of new algorithmic approaches were explored. And that's about when people started to really explore how can we use different types of DNNs in speech enhancement problems. Speech enhancement was the second big problem. One problem that drove DNNs, I think, was the whole image recognition. The other big field was speech processing that really contributed to the huge progress we made with the application of DNNs. And hearing instruments were pretty early also looked at. So around 2010, 2013, people started using DNN-type algorithms of various sorts to apply to hearing care, to hearing aids, and to the problem of speech enhancement in complex listening conditions. And there is a very nice paper summarizing a lot of this work and also a lot of the challenges that Brian, who is here, also co-authored. And basically in this paper, the authors summarize the complexity and the problems that we are facing when we want to integrate powerful DNNs into hearing instruments today for the problem of speech enhancement. And one of the first problems is that in order to really gain a lot of benefit for enhancing a speech signal, typically a large-size DNN is required. And that in turn requires quite a lot of computational power, which today, in many of today's hearing instruments is difficult to have. Also, when you have a large-scale DNN, the computational complexity leads to an acoustic delay. And Brian talked about the negative effects of long delay, especially when you have open fitting. So you need to have a complex DNN, but you need to compute it very fast, and it shouldn't introduce any long delay, because that's a problem for hearing instruments, and the delay should be less than 10 to 15 milliseconds to not be audible and disturbing, depending on the situation. And if you have a DNN of that size, one of the challenges for sure is how do you train it? How do you train it with enough sound samples so that it generalizes to really all the environments a person encounters in daily life situations? And finally, the problem that Brian also touched upon, the real-life application and how much benefit do you really get out of a hearing instrument when applying a DNN. When you have an open fitting, you have a lot of direct sound. And Brian reminded us that it's not only about the beautiful signal processing that we put in, but that we lose a lot of performance when we don't have a good acoustic coupling to the ear. So some really basic things that we also need to consider in the design of the hearing instruments. I think we have made significant progress over the past years, and nowadays we have a number of brands who have various forms of DNN-based signal processing being applied in the products with quite good benefit for the patients. The system that I'm going to talk a little bit more about is based on using a specific DNN structure which has been specifically developed for speech enhancement. It's not rocket science, new DNN architecture. It's been known to be quite efficient for the problem of speech enhancement for almost a decade now. It's a so-called UNet. It's a combination of convolutional neural networks and recurrent neural networks to reflect both the spectral and the temporal properties of the speech signals. The system, as is shown here, comprises different hidden layers. Here it's basically 13 hidden layers and a couple of skip connections. So that's the network that has been used and implemented. The publication is cited down at the right-hand side. At the end of the day, what we compute with this UNet is a mask that is being applied to the input signal to filter out and extract the target speech signal. And it's a complex ratio mask, including both phase and amplitude, to give a higher precision and a better performance. That's something that we tested, and the complex ratio mask, far more complex to compute, but provides significantly more performance. Now, the interesting thing is it's a speech enhancement system, not a speaker identification enhancement system. So, as we also heard earlier, it extracts the loudest speech signal. And that's a fundamental topic because typically it works really well, but it can go wrong if you have 2 or 3 loud voices and they are very similar. Then which one of the 2 is now the speech signal you want to attend to? The other problem is if you are talking to a person who has a soft voice, a child, or your wife, or somebody who has a softer voice, and you have a strong, loud voice coming from somewhere else, the system would focus on the strong voice. So these systems have potentially huge benefits, but potentially also some limitations. These are things that we can learn and we can overcome by applying directional microphones, by training the system to focus on a certain distance as well. There are solutions to that, but in general, these systems provide advantages, but also certain limitations based on the assumptions they come with. Also, when you have a system like that with still several million parameters in this network, it's computationally quite expensive to have in a hearing instrument, given today's computational power. And I have a plot here that shows the power consumption, the computational power of a solution as a function of the electric power consumption they have. And you basically see the power consumption of a lot of devices. And typically when you look into microelectronics, you see the spot, the big bubble that is called very low power. And that's when they have watt or some 100 milliwatt power consumption. For a hearing instrument, that's ridiculously high because the power consumption we have in a hearing instrument is around 1 to 10 milliwatts. So in the hearing instrument, we are basically down here in the power consumption constraints. And I had to smile when Sarah said that we are not applying these complex models. Yes, we are not applying them, not because we don't want, but because we don't have the power available in our systems to really compute them. That's a challenge. Now, if you want to have a hearing instrument with a powerful DNN, you have to have the computational solution that fits into this green zone. So you need to have a chip that is powerful enough and from a computational perspective, but power efficient from a technical perspective. And it's typically in the hearing aids, very specific chip development. So you don't get them off the shelf, you need to develop them yourselves. That's a major challenge that we are facing. Now, when it comes to training of this complex network, you have to train it with two considerations in mind. One consideration is the quality of the system that you want to achieve, sound quality and speech intelligibility improvement. That's one training criterion. And in order to do that, we have developed a method that used human subject ratings as an input to train another DNN that then served as the quality criterion. It's the Q metrics, and the publication is also listed down there if you want more details. But the other problem is you don't only have to train for the sound quality. As I said, we have pretty tough power consumption constraints. You also have to train the system to provide the optimal architecture and to meet the architectural constraints of your chip. So you have to have two constraints in the training procedure. One is on the sound quality you want to achieve, and the other one is on the architecture of your processing and the limits that you face there. So quality and computational efficiency are the two criteria that you have to apply when training this system. And you need a lot of different sounds from many, many different sound environments. We used available databases that you find today on the internet in order to have millions of sound samples that we can use to train the system to give us a good performance. Now, I spoke quite a bit about the technical considerations when developing such a system. Now I want to shift gears and talk a little bit about the clinical results that one can achieve when having DNN-based signal processing in hearing instruments with patients. One of the studies that we did basically tested the idea, and Brian talked about it earlier, of tested the impact of the acoustic coupling on the performance of the system. So we used a speech test, and we wanted to test open versus closed fitting. How much of the performance do we really lose, or can we maintain some of the performance, and do people still get some performance benefits when we change the acoustic coupling? We basically had people with a moderate to severe hearing loss, 17 adults, both male and female people, and they all had hearing aid experiences. In order to test it, what we basically did is we used an AC biotest, a test well known from the applications in cochlear implants. In English, we did that in Chicago. It's a low context with very realistic intonation and cadence test with different male and female speakers. We presented the sounds at various levels, 65, 67 dB and at various signal-to-noise ratios, individually based on the performance the individuals would have to achieve 70% intelligibility. Now, when we did this test, basically what you see here is to the very left from your perspective, you see the results for when the DNN is off. So left is the control condition, no DNN, and you see it for 3 different acoustic couplings: open, a vented dome, and a power dome. So open is open, vented is kind of half open, power dome is as closed as you can get. One of the problems with the acoustic coupling is that you typically have large inter-individual differences even for the different types of coupling. So closed might not be as closed as you think, and open might not be as open as you would like it to be, depending on the individual ear canal. In the middle, you see the performance when using a DNN at a moderate strength, and to the very right, you see the performance when using a DNN that the person could self-adjust in order to get individually perceived optimal performance. And what you basically see is, number one, you see quite a significant difference between open and closed. So when you apply a closed fitting, as we heard earlier, you get far more benefit. But what you can also nicely see is, despite losing performance because of the open fitting, with the DNNs or the noise reduction system in this case, you still get quite some benefit. The benefit clearly is always the best when you close the acoustic coupling more, but you still get some benefit and quite a significant benefit even if the systems are open. Now, in a second study, we also wanted to compare the performance of the DNN versus the classic noise reduction systems that we have in hearing instruments. And here we used different methods to assess the performance. We used a test that is called the CC-OLSA test. It's a speech test, similar like the matrix or the hint test and adaptive sentence test, where you have additionally a cognitive task. And the cognitive task is that you have a call sign. The call sign is a female name, Kerstin, and you have to always listen and repeat to what the person Kerstin said. And the call sign can jump between the 3 directions that you see here. It's done in an interfering noise at 70 dB. And the sentences that you hear are always co-located with the noise. So from the task, this reflects a dinner table conversation situation with the targets also moving around. So it's quite complex. We compared different algorithms, DNN versus on-off, and also compare it to the best noise reduction system we had before, a binaural directional microphone system, and the standard solution, the real ear sound, so basically the quiet condition solution. Again, people with a moderate hearing loss, and here you see the results comparing the results for the DNN versus the stereo zoom. And you basically see that the DNN always performs and adds roughly 20% of speech intelligibility in this specific situation on top of the directional microphone system, quite a significant benefit that we get. In the OLSA test, you have or in this specific test, you have a second task, and that is you can allow overlap between the speakers. So if the speakers move around, you can determine whether they have 0 milliseconds overlap or whether they have some overlap in when they start speaking. So they start speaking simultaneously. And that's kind of a cognitive task as well, because you have to switch faster and you have to separate 2 voices when they are on simultaneously. And in this task, it is measured how much overlap you can allow in order to get a good performance. with a directional microphone and the DNN-based processing. And what you can clearly see here is that with DNN processing, you can allow a larger overlap, and that's due to the fact that it extracts the target speech signal. And with the stereo zoom, you would have to move your head first. So it's more difficult, and you can have less overlap if you want to perceive speech well. So also an interesting result you have in terms of the cognitive demand, you have more reserve left. Also, when you have all the words come from different directions, like in a very fast-paced conversation, you see that with the DNN-based system, you are much better than with the classic directional microphones where you have to move the head quite a lot. Now, we tested not only speech intelligibility, but we also tested listening effort, and we tested it with two methods. One was a subjective scaling. We did that in 3 different labs in Shanghai, Toronto, and in Shanghai, in Chicago, and in Switzerland. And basically, what you can see here is the rating of effort as a function of signal-to-noise ratio for different efforts that a person puts in. And what you can see is that at the same effort, people can tolerate a roughly 3 dB higher lower signal-to-noise ratio, so they can tolerate more noise and still get the same effort rating with the DNN. So a significant reduction of effort when using these types of algorithms in the performance. We also repeated this measure, and this work was done by our Canadian team, and mainly driven by Jonathan Weisberg and Frank Russo and the team in Toronto. And they used a new method, functional near-infrared spectroscopy, to assess the performance of the DNN. And what we basically measure with functional near-infrared spectroscopy, you use light to measure the blood flow in the brain, and you measure the blood flow in the prefrontal hemispheres, which are associated with effort you have to put into a task. There is a nice publication by Weisberg et al. That presented this method. In this method, we compared DNN on-off, so we didn't have a control condition with a directional microphone, and it was a condition where you had a target in front and a noise in the back, so a very, maybe a little bit unecological condition, but we had to do 2 things: test the performance of the system and evaluate the method, because it's also a new method. And we had different programs, program for calm situations and the DNN situation, and we use different outcome measures. And what I'm going to show basically are the results of the blood oxygenation in the brain. And what you can see on the very left of this chart, you see in the brain area where you would expect a lot of effort to happen, you see a significant difference in the blood oxygenation between the program for calm conditions and the program that uses the DNN. So you have an objective measure of listening effort, and that clearly shows you that when using this system, brain seems to consume far less power. Now, we have to repeat this in more ecologic conditions, and we have to repeat it for sure and compare it with other noise reduction schemes, but it's very interesting to see that you can see something with such a method. That's why I wanted to present it here. And now I'm at the summary. I think applying deep neural networks can provide significant benefit to improve speech intelligibility in various daily life situations. I think what we have to do now is learn what are the best architectures, how can we apply the algorithms, how can we have more specific DNNs trained for more specific situations. So we have a lot to learn now, But in the first place, we can say that we benefit significantly from applying these types of algorithms. They come with a little bit of caveat, especially if you want to have large and powerful ones. You have to accept higher power consumption. You have to have very specific hardware architecture built in there. And they also, as we heard, come with some new challenges when you apply the systems, because they want to enhance speech, and that's independent of where it comes from. So we have to learn how to best apply them in daily life situations. But the clinical studies in speech intelligibility, in some measures of cognitive load, in measures of listening effort, have shown significant benefits for these systems in rather realistic conditions. And with that, I'm at the end. Thanks again for the attention and for the invitation.
Oh, thank you. That was great. Excellent. Thank you. We have time for some questions. Yeah, go ahead.
Hi, I'm David Rosenberg from 8th Nerve Consulting. Thank you very much for that great talk. One of the most common complaints that I hear from hearing aid users is wind noise. And I was wondering if DNN processing is robust to filtering speech in wind noise conditions, particularly for people who like to spend time outside. Thank you.
Yes, we haven't tested this algorithm. I know there is a couple of devices that have been specifically trained and optimized for wind noise problems. And there is also quite some work going on to now train DNNs and maybe smaller DNNs for specific applications. And one theme in this work is also to train the DNNs to perform optimally in wind noise. So it's definitely an avenue, and we expect quite a bit of benefit there as well. But we may have to have more training data and then optimize it for these situations. That's an interesting aspect. Brian mentioned that when he uses the DNN and sometimes his conversation partners are quiet, he hears the people at the next table. That happens to me as a normal hearing person as well. So we can develop a DNN to also only amplify what is, say, in a meter distance. That's also a training function. But then you don't hear the waiter anymore. So we have to learn about what are the compromises we have to take.
Thank you. So this has been, you didn't mention any particular product, I know, it's the Infineon Sphere is the device, yep. I think, right? But anyway, it is available as well, I'm trying to say. It's reality yeah. into an actual device. So.
Yeah, so, I mean, I would like to emphasize DNN processing is a field that all the manufacturers have been working on. Yeah. We have been working on it. We introduced products, but the other manufacturers and brands also have been working on it. Yeah. Also have products that have various different functions, but similar functions built in.
Yeah.
But this was a specific function, yeah.
Right. Great. Thank you for doing a good review overall. Yeah, one more.
Yeah, thank you for a great talk. In terms of the power consumption in using DNNs, is that comparable to what we need in a cochlear implant, or is it even beyond that? Just interesting to know how large the battery would be that you would have to carry around.
So, I mean, the DNNs that you see today, as they are fit in classical hearing instruments, and the hearing instruments consume far less power than what you have in a cochlear implant, this system and other systems that are available would fit in a cochlear implant. The power consumption here is significantly higher than in a conventional device, but it still provides several hours of use of this system per day, far more than what people typically use. So it's interesting that power consumption is a non-issue in the market today.
Great, thank you, Stefan.
Maybe Lars had
We'll have more time for a little Q&A later. All right. I hope. Pleasure to introduce you to Nima Mesgrani. I've followed your work for a long time. Used to work in Eddie Chang's lab at UCSF. I heard him give a talk at the Hearing Research Seminar at Stanford. I think you're a postdoc then. So it's great you've made amazing progress. I'm looking forward to hearing about it. Thank you.
Yeah, thank you very much, Sunil, for the invitation. It's an honor to be here to tell you about brain-controlled hearing technologies. But before I start, I also like to welcome the first-timers. I came to this meeting exactly 20 years ago, and that's me, with Stephen David proudly holding the abstract book from ARO. Yeah, I had a lot more hair and a lot more hair cells back then. All right, so this is the problem that other speakers have already talked about, which is the problem of speech perception in multi-talker scenarios. And it's a difficult task, especially for people with hearing loss. And the solutions that we have today are not very good. And there is not much we can do unless if we have some information about what the person wants to listen to. Right? Without that, with just signal processing, it's very little we can do. So this is the idea of the brain-controlled hearing device, which Torsten also introduced, which imagine that if you're in a cocktail party and you have a hearing loss, you don't want it to amplify everybody, right? You don't want to have every sound source. You want it to just amplify the source that you're interested in. And if you switch your attention to another conversation, you want this device to automatically detect that from your brain, right? And to switch the amplification to the other speech stream. And that motivated this idea that maybe we can have a device that is basically looking at all the sound sources in the environment, comparing them with the brain of a listener, and only amplifies the one that is most similar to the brain. So this is called auditory attention decoding, or AAD, and it's something that is not very new. The very first implementation of it that we did was more than a decade ago in this workshop, Telluride Neuromorphic Engineering workshop with Malcolm Slaney, who's also here. So back then, it was a very primitive version. We had actual people reading instead of speakers, and they were holding signs to tell that, where the person needs to focus their attention. And, to some degree it was possible. You have these things that basically try to show where the attention of the person is. But the reality is that this is more than a decade ago, and we still really haven't shown that this can be a viable technology, right? We still don't have devices that put this in real use. So why is that the issue? One problem that I would like to highlight is that we as a field have been focusing too much on AAD accuracy, and to some extent ignoring the behavior. And there have been a lot of efforts since then that have been using either invasive electrodes, scalp EEG, in-ear EEG, around the ear EEG, and they all have been showing that the improvement goes up as you choose better and better methods. But the problem here is that we don't really know how much is good enough. In other words, there is a threshold, there is a usability threshold that we haven't really explored. And we don't know exactly where that is. And I think that's very important because it can tell us that some of the solutions, like maybe the in-ear solution, may never be good enough. Like maybe the signal quality could never be enough to reach that usability threshold. So what I think is missing is a direct connection from this to behavior. And pretty much every AAD paper that you see out there only reports the accuracy, and they stop there. Right? They don't try to relate it, and we actually, our papers too. We never try to relate this to perception. And I think it's very important, because if we have a curve like that, then there is hope, right? If we do enough, we're going to pass through that difficult part of the curve, and now we are in a regime that's useful. But if the reality looks like that, then it's a very difficult problem, right? It's a very different thing, because we have to then, be, good enough to make this useful. So 3 questions that I think are difficult in this area, and I'm hoping to address today in my talk, are the following. So another thing that we've been ignoring is, would this even work if the speech is not intelligible, right? So that's the promise, that if you go to an environment, speech is not intelligible, this could help you. But in that case, can you even decode that from the brain? So it's the chicken and egg problem of AD. The second thing is to really put a bound on this and say, this is enough. If you tell me that your algorithm does 70% correct, what does that mean? Who would it help, and under what listening conditions? And finally, this sort of a real-time and closed-loop systems, there are many attempts at trying to implement those, including the one that I showed you from 2014. But can they actually help a person? So the focus, hopefully, in this talk is going to be only on the behavior and trying to get more deeper into that. All right, so here's the first problem, which I call the chicken and egg problem of intelligibility, which is if a speaker is not intelligible to begin with, how could you even decode that from the brain signals to amplify it? All right, so that's a problem that I think we've been ignoring. And we've done some work on that. We just published a paper that we looked at the scalp EEG, and we have people listening to speech, and we changed the signal-to-noise ratio or target-to-masker ratio of the attended talker from very low to very high. The good news here is what we find is that even when the attended talker is very weak, the task performance is maybe down to 25%, which means that you can only hear 1 out of every 4 words of the talker that you want to pay attention to. Even at that low intelligibility, it seems that the neural signature is good enough for us to be able to detect it. So that certainly is good enough, right? Good news, which means that if you go to a scenario, the attended talker is barely intelligible, that's good enough for your AAD to pick it up and amplify it to the level that it's now fully intelligible. The second problem is this issue of the trade-off. So we want to amplify the attended talker to make it more intelligible, right? But then the cost of that is that the other speakers that are in the environment are going to become softer and softer. And at some point, if you are not able to switch attention anymore, that would be also a big problem for this sort of technology. And the second thing is this mapping from the AAD accuracy to behavior. So we want to be able to characterize that. So what I'm going to show you is the result of a large-scale study that we recruited 1,200 participants, 600 with normal hearing and 600 with hearing impairment. All of it is done online on Prolific platform, which is similar to Amazon mTOR. And these people are going to listen to simultaneous conversation as we change the parameters, and they report their preference, and we ask them also intelligibility questions so that we can evaluate exactly what they listen. We also ask for their audiograms. So we know that our hearing impaired listeners, they have a range of audiograms, so we are able to define 3 categories, HL1, HL2, and HL3, based on the average hearing loss of a person. All right, so what do we find? So this is the first experiment that we have 2 simultaneous speakers, and halfway through, the participants are prompted to switch attention. In some of those trials, we go from soft sounds to loud sounds, and in some other trials, we go from loud sounds to soft. And what we find is this very nice trade-off. So this is for normal hearing subjects. And as you can tell, if the target speaker, if they start with a loud sound, their intelligibility, of course, is higher. But there is a trade-off, right? Switching to the other speaker becomes more and more difficult. The same kind of trend also persists as you go to HL1, HL2, and HL3 subjects. So the interesting thing is that they all can reach maximum intelligibility if you amplify the talker enough, right? But it comes at a cost, because now the talkers that are the subjects that have a more profound hearing loss, it becomes more and more difficult for them to switch to the other talker. So what is if somebody comes with an audiogram and you want to give them a brain-controlled hearing aid, so how do you define how much you want to amplify the attended talker? So this gives us some clues. if we define that as we want to amplify so that at least they have 90% of their maximum possible intelligibility, then we find that the amplification of the attended talker is actually very linearly related to the average hearing loss of a person. So, so this is important because this is a design parameter, right? If you want to actually make it into a device, you need to be able to choose that, and this gives you a way to relate that to the audiogram of the person. Now, at that level, normal hearing and all of our hearing loss subjects, they are able to perceive the attended talker at the same intelligibility, about 90%. But obviously, there is a cost, right? There is no free lunch. So as the hearing loss increases, we see that the intelligibility on the unattended conversation goes down. And also, the ability to switch becomes more and more difficult. But the good news here is that if you look at the lowest intelligibility on the unattended stream, it's still above the chicken and egg threshold. Right? So even for the people who have profound hearing loss, and with this amplification of the attended talker at 90%, we still have enough to be able to detect their attention and make the switch. So that's another good news that comes from this behavior. All right, now the next experiment is this sort of AAD accuracy and how it relates to behavior. In other words, if you give me two algorithms, one of them is at 60%, let's say it's using in-ear EEG, and the other one is at 95%, maybe it uses intracranial EEG. So we want to be able to relate those numbers to actual behavior. So we have this experiment that we go from system off to system on, and we simulate different AAD accuracies. So all of this is, by the way, simulation. There is no neural data here, but we're just simulating as if we had the neural data, but it's with different amount of noise. So when we look at the preference of our subjects, for normal hearing and for hearing impaired, we see that they all prefer to have the system on. And that is related also to the target to masker ratio. And these two seem to show a relationship, which means that if the situation is very noisy, if the speaker that you want to pay attention to is very noisy, you are willing to also tolerate more inaccuracy in your AAD. When we look at their intelligibility improvement, we see that the normal hearing don't really gain too much, even though they prefer to have this. Maybe it reduces the listening effort for them. But in terms of intelligibility, they don't see a big boost. The patients with subjects with hearing loss, those are the ones that actually see a very big improvement from this AAD. All right, so now the final thing is this sort of the real-time auditory attention decoding, right? So we have all of these implementations of the real-time closed loop, but we really want to now put this to rest, that if you could do this, what is it that you want to know, right? So there are we identified three behavior problems that are very critical. And by the way, this is our setup. So we have a person, these are epilepsy patients in the hospital. They have implanted electrodes in their head. We look at their brainwave, we reconstruct the sound, compare it to the sound sources, and amplify the one that they seems to be attending to. So here are questions. The first question that you want to know is, do people prefer the system? Like if you turn it on or off, which one do they prefer? So for this task, we ask them to pay attention to one of the streams, and halfway through, we turn on the system. So we do the comparison within the trial, and we ask them, do you prefer it with on or off? By the way, obviously, they don't know. We don't tell them anything about what the system is and how it works. So we keep it blind. We just tell them, do you prefer segment 1 or segment 2? The second thing that you want to know is this thing that, are they able to switch attention? Right? So if you amplify the attended talker, are they still able to switch their attention? In the early days of this in 2014, we had this joke that, if it doesn't work, we just you just shake your head a few times, and then you reset the algorithm so that you can now attend to a new person. But obviously, that's not good enough, right? So we want to actually check that. So here we have an instructed attention switch halfway through. And the third thing, the final thing is, in the real world, people are doing this at their will, right? So they should be able to self-initiate the attention switch. So we tested also this system with that. And now I have a few videos to show you. I hope the sound is working. This is the part that I need the sound. So here's a video of a person. There's like two conversations happening, and here we tell them that your job is to pay attention to the talker on the right side. Halfway through, at that line, we turn on the system. And at the bottom, you see the decoding accuracy.
And other annoying noises. Not to mention there's so much dust and pollution here. I hope to be able to move out of the apartment soon. My top choice would be a big house in the countryside with a view of the village, trees,
In my case, my mother has been an extraordinary influence on my life. The one trait of hers that I value the most is her enthusiasm for learning. There has never been a night I went to sleep without learning something.
So I hope you were able to hear how quick it works and how what you get that. So we of course we had a lot more trials like this. Here you see the attention, the decoding accuracy for each one of them. But as I promised, I want to focus on the behavior. So here we tested their behavior. Their preferred trials significantly is higher for the on condition. And also when we check their intelligibility, all of our subjects also see a significant boost when we turn on the system. So moving to the second, and we also see that their listening effort, as measured by the pupil dilation, goes down. So when the system is on, they are spending less effort, which is also useful to know. All right, so the second experiment was when we instruct them to switch attention halfway through. And here's an example of that trial.
Bread. The baker said this was his first time trying to make it, and he said I could have it for free.
Oh, this bread smells amazing. It smells so sweet. I don't know whether to be happy or not. I was trying to cut out all bread from my diet.
What would make you think he did a bad job?
Well, I am not a repairwoman myself, so I'm not sure if my opinion is valid. That being said, I don't think he did a great job because, once again,
Yeah, was it I don't know the acoustic in this room, but I hope it was obvious how it works. And again, we had many more trials like that, and you can see that very clearly, very quickly, you go from speaker 1 to speaker 2 after they switch attention. And their behavior, so if you notice, there were some repeated words in each conversation, and their job was to press a button whenever they hear a repeated word in the attended conversation. And you see that there is a successful switch, so they are able to behaviorally also, we have confirmation that they're able to switch easily from 1 to 2. And here is now the third experiment, which we ask them to freely switch attention, but of course, because that we want to know where their attention is, we ask them to point to the speaker that they are paying attention to. So this is the case that this subject is starting with the speaker on the right side.
Help me get it hauled to the repair shop. I tried pushing it there, but I don't know if my back could last the 10 miles. I pull it with my car, but that's
It won't be any trouble to cancel your subscription. However, I do have to ask, are you sure? Even if you don't do woodworking any longer, we recommend you keep your subscription as you receive coupons on materials and tools monthly.
Yes, I am sure I'd like to cancel my subscription. As for my payment, how about you buy me one of those cheap pizzas and a couple of beers, and we call it even.
Yeah, so it also works great, and they're able to do that. And of course, the important question is that these are the first people who are actually using this, and they are, what do they feel about it? Right? So here is some conversation with the patient. After we've done everything, then we tell them what's happening. We tell them that this is this thing that you're doing, and we ask them about how they feel about it.
How do you feel about this?
Science fiction.
You are confronted with your brain.
No way, really?
Yeah.
That's wild. Yeah, because I was sitting there and I was like, it starts out kind of quiet, and then all of a sudden this one dies out, and then this one goes really loud.
You did feel the amplification when you were trying to focus on one talker and then suppression on the other talker, right?
Yeah, that's pretty clear how you're doing it.
All of a sudden in the second section, what I was listening to was louder, and the other thing was quieter. And in the first section, they were both equally loud. That's dope. That's super dope.
I think it adjusted pretty quick. Yeah, I think it adjusted pretty quickly.
So do you think this kind of technology is going to be useful?
I think if you could really implement it in the hearing aids that you guys is the goal, it would be really helpful to just be able to have someone who's hard of hearing be able to kind of pinpoint to exactly what the conversation they want to have, right? Especially if they're in a location from other people or something.
So it seems like they are satisfied. And, and here is a final test that we did. So we said, if this actually is working, what if we go and we try to reverse it? So now, whenever they try to pay attention to a talker, instead of amplifying that, we try to suppress it. And this thing, after a couple of trials, they all get very angry. And here is a conversation with one of them.
That when you change attention, then you lower the volume down. Esto es lo que están haciendo estos tramposos. So that's what they are doing, these cheaters. Well, we are not doing anything, it's our brain. Dice que ellos no están haciendo nada, que es tu cabeza.
No, sí, te rebajan el volumen. Le baja el volumen a ese.
So she couldn't believe that. She thought that we are trying to mess with her. And one good thing, interesting thing also to point about this particular subject. This subject had zero English comprehension, and all of our stimulus are in English. So that's another confirmation that even without understanding a single word, this was still working for her. Almost as good as it was working for people who comprehend English. So that's another good thing, that intelligibility is not required for this sort of technology to work. All right, so just for the last part, I wanted to also focus on something. This is the dream that we've been following for a while, right? To be able to connect the brain to the hearing aids. And while we've been busy on this, a lot has been happening in this field that you might have heard of it, which is AI. And now we have these amazing technologies that just in the past few years, we now have this sort of AI agents, auditory AI agents, that are able to process the sound in very amazing ways. Like you can basically, you can have an AI agent, that auditory agent, that is listening to the environment, and you can ask all kinds of questions from these. So, I think the future of where we have to take this is to go from this sort of a brain-controlled hearing to brain-driven auditory AI agents. And we have a first effort in that direction. We have a poster here at ARO that, feel free, if you want to learn more about it, you can go. So here we have the scene that goes into one of these big foundation models. Here we're using the state-of-the-art model from Alibaba, a Chinese company called Qwen 2. The user can interact with that model, and also we try to implement and put the brain signals into these systems. And the result is amazing. Like with this sort of model, after you take this model and fine-tune it with the brain data, then the subject can extract the speaker that I'm listening to, and it just give it to you. You can say, transcribe the speaker that I'm listening to, and the model starts to transcribe the attended speaker. You can even say, I've been talking to this person, and I just wonder if there was something in the background that I didn't listen, but I should have. And then it can basically give you a summary of all the background conversation that has been happening. It can do translation. It can do pretty much, like anything that you can imagine. Like these sort of models are able to do, and I think it's very critical that we think about how we can also make them listener aware. We can put them, integrate neural data into this sort of thing. So this is just a confirmation that shows that, if you get this model, give it the mixture audio, the output is not very aligned with the listener. If you give it the oracle, which is if you extract the attended talker and give it to this model, you get the upper bound. And when we try to do this, when we try to integrate the neural data into these models, we get something that is very close to the oracle. All right, so just to summarize, I think what we need to do is, we need to focus more on the behavior in this sort of AD research, and really try to optimize for behavior as opposed to just detection accuracy. And we need to, have a better definition of what success looks like. Who does it help? Under what condition? And is everything we're doing, like this sort of one electrode in the ear, is that viable, or is it time that we need to think about new strategies that is necessary for this? And the final thing is this movement from brain-controlled hearing aids to brain-driven auditory AI assistants, because these models are going to just get better and better, and they can do amazing things. So we need to think about those. And I would like to thank all the people who were involved in the work that I've shown today, and especially I'd like to highlight Vishal which has done a heroic job making all of this happen. This is not easy to do, and I'm very thankful. And thank you very much for your attention.
The future is here. Oh yeah, go ahead.
So, Nima, thank you very much.
Oh, something went off.
It's off.
Go ahead.
Somehow. No? No, okay. So did you eventually recognize a difference depending on which ear, left or right, having in mind that you have attention either left or right? Did these subjects distinguish, or could you see a difference if they liked it or not, your model? Did you understand? Could you trace it down if the left or right ear was more or less affected? Looking to if attention is left or right.
In the brain, like left?
Yeah. Could you trace it back?
Yeah, no, so we have different coverage in different patients. Some are more left-sided, some are more right-sided, but we don't see a very significant difference between, for attention decoding from the left or right side of the brain. We also have done some work, and we have a couple of papers that we look at spatial audio or spatial attention. Like if your attention shifts in space, there you have some contralaterally tuned sites that are modulated differentially if the attended source moves in space, for example. But if the purpose is just decoding, we don't see a big difference between the two.
Go ahead.
Thank you for great talk. And maybe it's related to the previous question. And you, in a demonstration, you instructed the patient to just direct attention to left and right. But do you think that the demonstration works equally well when you instruct the subject, for example, attending to female or male, and kind of if there is no spatial distinction?
Yeah. All of our previous studies are with co-located speakers, and it works great in terms of the attention. The only reason that we had a little bit of a separation between them in this case was for a practical reason, because we wanted to be able to, we have conversations. In one of the examples that I showed, we have two male talkers talking at the same time. And we wanted to go beyond just like male and female, which is an easy case, right? So we wanted to have also same gender conversation. So we had to create some kind of a cue so that people can be instructed to conversation one, conversation two. But yes, it works for co-located for sure.
Okay, thanks.
Sure.
Go ahead.
Hello. Thank you very much for the talk. I have a question about what happens with your clinical trials if you take the visual input aspect from your patients. Are they still able to switch sides? And, yeah.
What do you mean by visual input?
So like in a real life situation, I could want to listen to the left without actually looking at the person, or the right without actually looking at the person.
Right. Yeah, I mean, we didn't really explore audio-visual in this case. We didn't have a visual. But, as I think Torsten mentioned, that if you have also visual cues, it definitely helps more, right? Because if you're able to lip read. So that definitely is a direction that we would like to explore more in the future. But so far, we've just been focusing on one modality.
Thank you.
Thank you.
Thank you very much for the great talk. I'm Cinziana Wenzel from Homburg. I have a question regarding the patients. Did you look on their hearing abilities? Did they have any sensorineural hearing loss, for example, that could be correlated to the results that you would look at?
So these, I'm regretting deleting a slide that I had. So, so the patients that we had, they all had self-reported normal hearing. But what we did, we took this audio and then we played it to many subjects offline, who had different degrees of hearing loss. So it's not the same thing because it's no longer a closed loop. We just say that if this was the audio that you heard, which one do you like more? And there we see that there is a big improvement also, and it's very much correlated with the hearing loss. So as the average hearing loss increases, the benefit that they see and the preference that they have for the system increases also. But with ECOG, it's very difficult to study that because we don't get, and we have no control over the patient population.
Okay, so you didn't do any hearing tests on the patient before you did the rest of the test. That was my additional.
No, we rely on self-reported normal hearing. None of our patients reported any hearing loss.
Okay, thank you.
Sure.
Last question for the speaker, and then we'll have the other speakers come up. We're going to ask everybody questions.
Thank you for the fascinating talk. Perhaps I missed this, but I was wondering if your decoder is robust to using an EEG set with normal population that's not this epilepsy population with the internal electrode array.
Would the decoder work with normal hearing, without epilepsy? Yeah, I mean, so we, in our EEG papers, we use the same method that we have, and it works with, with people with normal hearing, as Torsten showed, also with people with hearing loss. You might even get better. But unfortunately, when you're looking at, invasive implants, then you are, you don't have that much freedom. You can't look at it in people who don't have epilepsy. We usually exclude the sites that are then, planned for resection from our studies. So we are trying to at least, look at only the sites that are normal, electrode sites that are normal. And, and I have this backup slide that, this sort of, we call invasive, but this could also really, there are different degrees of invasiveness. You could put electrodes in the vein. You could put very tiny slits through the brain. You could screw something that gets very close to the brain, but doesn't even penetrate the. So we are, trying to look at these things and see if we can collaborate with these researchers to see which of these modalities would be enough for this. Right. Thank you.
Thank you. If I could ask the other speakers to come up, please. Mara, Brian, Torsten. Stay up. And yeah, you stay up. Yeah, thank you. So I'll open up the floor to ask questions you may not have had a chance to ask. For the other speakers, synthesis of questions you've thought about, feel free to go to the microphones and you can ask each other questions if you like, or whatever you want. Anybody? Anybody? Alex, are you going to ask a question? Oh, no, you can ask a question. There you go.
Hello, Alex Osels here. So interesting morning of education. So I was thinking about the occluded versus open ear canal, I guess hearing aids. Has anyone made a hearing aid that's adjustable, such that if there are benefits to being open some of the time, it would occlude some of the time, and yet something with neural networks might be achievable?
You want to take that? Like a MEMS transducer that would open and close it. Yeah.
Of course, I'm thinking piezoelectric, but
yeah. Do you hear me? It's working?
Yeah.
So yes, that has been tested, and it's been an age-old problem. Physically, it's possible, but the problem of these systems is the reliability in daily life operations, because this is a super small mechanic, and it has been tested. It also has been introduced, but it's basically too sensitive. It's working quite well, if it's working, but it's not reliable enough for daily life operations. So we have to improve the mechanics and the physics of such a delicate mechanical system that can open and close. And the other approach that Brian also mentioned is to do it with active control. And then you have active control systems that can provide an open ear perception. They typically require larger loudspeakers than what we apply in the hearing instruments. So if we make large compromises in terms of the size and the design of the devices, then this is definitely something that is feasible. So I would say this is a pretty active field of research and technical development in our field.
Thank you.
And Brian mentioned Apple already has something like that. Yes, they have active noise cancellation and things. The problem really becomes when you have to apply a larger amplification for a more moderate hearing loss than what they have today. Then it becomes challenging again for the whole microelectronic design. So a lot of technical challenges to be solved, but it's definitely something I think that is in the pipelines.
All right, thanks. Next question.
Well, thanks for a very interesting session. I think my question is mostly for Sarah and for Stefan, but it's about the generalization. We work with these DNN systems ourselves, and generalizing the speech is perhaps not so difficult, but generalizing the noise and making sure you don't get strange behaviors in specific situations. What are your thoughts on that?
So I'll start with so the way that we're using the DNNs is really as a computational method. So if the models are trained with speech, they generalize well to other stimuli, and basically it's just a faster way to compute these models. Then of course, when the model is fixed and you train the hearing aid, then working with speech corpus is sufficient for the moment, but I think we should see how well that goes to music and things like that. We didn't see a benefit training with speech and noise versus training with speech alone in one of our first sort of experiments in that, but we should definitely explore that more. One of the limitations, for example, is that speech corpi for our type of modeling, they need to be at high enough sampling frequencies, like 20K, so that also our learned gain will apply there. So there are limitations related to the training data that you use. But I think for what we do, it's much less of a problem than maybe for noise reduction systems that apply to much more scenarios. Do you want to comment more?
Yes, from my perspective, one of the big things is regarding the noises to have, again, enough training examples. So that's one thing, that we built a huge database of sounds and then a lot of combinations between different speech sounds, different environments. So large enough training sample. The second thing is the way we apply the system today is mainly in really loud noise environments, for which we have also good samples. So we limit the application, and we haven't had any issues with the system doing funny things, hallucinating or whatever. But maybe it would happen if it would be applied in much more quiet conditions in daily life environments. And that's something to be learned and figured out.
Excellent, thanks.
Can I ask you maybe, Stefan? You talked about your DNN-based as a noise reduction system, in particular, that it works in cocktail party setups, maybe not in various speakers, but let's say other backgrounds. But what was actually your training? You didn't touch upon it. So how huge was the database? How variable did you choose setups? Or was it just the more the better, or did you look at really different setups? So how did you define that, and how is generalizability?
The training database it's described in the papers, and the question is always, people always argue how many samples they use, but then the question is, was the sample an hour or was the sample a minute? We used huge sound databases, and training typically took weeks and months to perform, and we always tried to have different databases combine speech signals, background signals at different SNRs. So it was a huge database, 10 million, 14 million, 20 million sound samples. So again, depending on how you count it. We try to be super sensitive to have a broad range. We collected a lot of sounds from publicly available databases and then trained the system.
That's the problem with these as a DNN-based. This is all fantastic, and we are going this direction. But of course, if you don't have huge amount of data, then you are, by definition, more limited, and then you need some constraints or some other additional information to make it more robust. Otherwise, robustness is given by a huge amount. But if you don't have that, sometimes, then what to do, right? How to create robustness. And then you need some conditions or sometimes knowledge-based input which makes the system more robust, such as less can be more also. Just...
I just make a comment about the point that Stefan made. What happens when the processing is active and you're not in a very noisy situation? And I've tried that a few times. I manually select the sphere processing, and it doesn't seem to do anything especially bad. Under those conditions, I still hear environmental sounds, and they don't sound especially distorted or unnatural.
So I mean, in general, I think one of the big steps from taking something from the lab to a product is to make it really work robust. So we apply the system in a rather conservative way, and I think that's true for all of us manufacturers. And the second, we put a lot of effort in avoiding artifacts. So we do an awful lot of testing, not only testing when it is working well and trying to prove that it's working well, but even far more on testing that it doesn't do anything wrong, because that's usually a disaster.
That's all. Yeah. Training is definitely an important issue to consider. Next question.
Thank you. Thank you for a great talk today. And I apologize if I missed this, but could someone explain to me in simple terms what a neural network model is, why it's considered deep, and why everybody is going in that direction instead of other machine learning models like support vector machines or even simple linear or nonlinear models? It seems, I don't know this area. It was great to learn about it, but I'm missing the neural network information.
Let me see if I can, that's a big topic for sure. Hard to answer in an elevator type pitch. But this gives me an in to answer that question the following way. There are a bunch of seminars and at this meeting that are going on. I suggest you attend it. There's lots of posters, obviously, on machine learning and AI that are this afternoon and tomorrow. This whole meeting, actually a lot of stuff on hearing aids as well. So I would say that's, if that's, I know it's not a satisfactory answer, but that's probably as good as we're going to get at the moment. We could talk at lunchtime as well.
Thank you. Thank you very much.
Yeah. Mario?
Hi, Mario Sfersky from NYU. First, let me congratulate you, Sunil, for this amazing session. There's a lot of things that I loved about it. One of them was the contrast between the wave of the future that Sarah and Nima presented with super exciting stuff, and the hardcore engineering perspective provided by Torsten and Stefan. I think it was Torsten who said about one of the approaches, can we implement this? I don't know. Because you're interested in whether these approaches can be implemented in a real device that people can use. So I want to follow up on the last question to Nima, which is, to what extent will the exciting stuff you're showing can be implemented with surface EEG? Because if you have to move on to more invasive approaches, of course, that makes things less interesting. And let me say, by the way, that I love what you've been doing in terms of trying to assess usability and the benefit of using this approach in many interesting, ingenious ways. A lot of that work, however, has been done by necessity on epilepsy patients with the much clearer signal that you can get from brain surface electrodes.
Yeah, thanks for the nice question. So, yeah, or maybe you wanted to respond. Sorry.
We can start with
you start there.
Okay, well, I guess, so your question was the motivation for the research that I talked about. Because, every single time I talk about this invasive thing, I get the question, like, do you have to do it? Can you do it with in-ear EEG? Can you do it with around-the-ear EEG or the scalp EEG? And that's why we thought about what would be the right systematic way to answer that question. It would be to actually try to measure a threshold, a usability threshold that is required, right? What's the minimum signal quality that you need to have? And so we are working on the behavior side. Another friend of mine, our colleague, Behtash Babadi, did some really interesting work that they tried to put some theoretical bound, Right? So if you have your signal, and if you repeat the same thing multiple times, then just from the signal itself, you could put a theoretical bound. Like, this is the upper bound. This is as good as it gets. Right? So if you have that from that work, and if you have this threshold from the behavior work that we're trying to do, then comparison of the two will tell you that, this signal could never get good enough for this system to be usable. Or maybe, yes, maybe if there is theoretically you can get there, but you're not there yet. So do more, neural networks. So that's our approach to that question.
Thank you very much.
And just very quickly, I want to add that, this sort of invasive recording is something, I will look at it something like a DNN, that, at the moment, we know that eventually the computation cost is going to go down. Yeah. Right? You see it in something like DeepSeek that suddenly comes and says, no, you don't have to have that much power. You can just, so these things are going to happen, and so I think Sarah is doing a wise thing by looking at the future and say, that field will get there, so I'm trying to be ahead of that. And I think the same thing will happen with this sort of invasive recordings, that in a few years, my hunch is that it's not going to be as big deal as you might think about right now. A lot of companies are trying to work on these sort of alternative ways that minimally invasive, invasive but not too invasive, not a big opening. So I'm betting on that also, that will happen.
I want to ask Mara a question here. So you've taken us through a historical tour from the birth of an acoustic, the carbon microphone and transducers, to hearing devices of all sorts. And here we are, sort of very futuristic type. What's your perspective on these new technologies you've been hearing about today? What do you think?
Actually, when you met me at MOH with Michelle Friedner, and we were giving talks on cochlear implants, this is an anthropologist at University of Chicago who I collaborate with quite a lot, who uses implants herself. Mm-hmm. We actually are editing a book on cochlear implants and brain implants right now, and so anyway, I hope to talk to you a bit more, because we have 50 years of anthropological data on cochlear implant use, and obviously the kind of technology that's been used but never FDA approved for certain kinds of brain implant stimulators is very different than cochlear implants. But sometimes there's a very, let me put it a different way, sometimes there's a very long now. And I think with brain implants, we've been in the future that hasn't quite been realized for half a century. And it's a very interesting moment to think that there will be commercialization and FDA approval for different kinds of implants really are on the horizon. That seems like a big shift in this long, long now. So this is something we've been working on a bit. Then there's certain problems that never seem to go away. Batteries, like power. The power thing is such as that, from the beginning of the 20th century, you just have this repeated hiccup, complaints from users, expense. So yeah, that's just, where are those people? They need to come to all of the portable consumer tech meetings. Yeah, so there's a few things, and then the cocktail party effect has just been, maybe we're about to surmount that, but that, as a historian, that's just from the minute that like Colin Cherry named it, and even before it was named, that's just been a constant complaint. So if those two things, if those are solved, that is like a century of like user complaints.
Right. You feel like we're, based on what you've heard today, getting any closer, you think?
It sounds, well, and maybe not the battery issue.
Not the battery issue.
The power issue, like we're circumventing it. It sounds like what's happening is instead circumventing it through different processing methods, but not actually solving the power problem itself. Yeah. I'd have to go to like a materials science conference to figure out if that. I know there's so many different components to this. All I can say is certain things that have seemed like a long, long problem, I do have the feeling that a big shift is on the horizon, and then there's these other things that seem to still be lasting.
Yeah, absolutely. Thank you. Yeah.
I just briefly wanted to say something about the power consumption. I once saw a nice chart showing the development of the power capacity of batteries over the past 100 years and the explosion of computational power that microelectronic brings. And one goes linear with a pretty shallow slope, and the other one just is an exponential function. And it's just a physical problem, and I don't know why, but when I look at the battery capacity and the increase over the past 30 years, it's just ridiculous. So I'm afraid this problem won't go away. Yeah.
Can I have a quick comment to the last question? Sorry, Bob, just the last question related to the closed loop EEG. And so, because you asked also, is it really feasible and so forth. So I think it's fascinating what has been achieved already. Or I did not expect necessarily that it works within a couple of seconds, let's say, to have this feedback and to have that closed loop system working. But of course, what Nima said is very crucial to really connect to perception, not only read out decoding accuracy or something. This number is informative, but it's not really telling a lot about how does it actually work in, or the connection to perception. That's true. And even further, I mean, I would say what really needs to be done also is, okay, you have these particular patients which have, of course, which are exciting to work with. But let's say if we go back to normal hearing impaired people who may have electrodes here or in the ear, this is probably too noisy, but then what's also not clear is how does it work actually if you have this system, how do people communicate then in a real setup? So do we learn to use this closed loop system? Can we learn, can we train it, so to speak? How does our behavior change with that? So to speak, we have no clue, right? So I would say it is, it's fascinating that it all worked, and it's fascinating that we have some robustness, so to speak, in the hearing impaired system, but there are so many questions and probably question marks, but potentially there's also something we can operate with that system with time or by training in a way, so to speak. So there's maybe something.
Yeah. Well, I think, I know there's more people wanting to ask questions, but we need to wrap this up. So I want to thank all of you for coming, attending, and staying to the last bitter minute, and all the amazing speakers. It's been a great session. Thank you, everyone. We can come up and ask questions if you want.